Okay, so today's lesson is for Tuesday, November 1st, 2011. Today you'll be taking some notes. As always, really important that you fill in any blanks in your notes. Today you will actually be handing those notes in for a participation grade, so it's important that you leave those with the substitute so that I can give you a participation grade for them. Over here on the right side, there's a link to where you can access these notes if you lose your copy or are absent. After we go through these notes, we're going to go through them in PowerPoint. You'll be given a handout, and this is the uniform circular motion problems go with this handout. You'll be doing as much of that in class as possible. Whatever you're not able to finish, you'll be taking home for homework. If you have any questions, because I'm not going to be here today, it's going to be important that you email me if you have any questions. That way I can get back to you and make sure you understand what you're doing for homework. All right, so let's go ahead and get started again with this uniform circular motion notes. So let's get this PowerPoint going. All right, so what exactly is going to be on this upcoming exam in regards to uniform circular motion? Well, you're going to have to know the important concepts that we cover and demonstrate in class. We're going to have a lab tomorrow, so stuff like that will be important. The important conceptual stuff that we're going to talk about today with regards to radius of a circle and how that affects speed, velocity, and force. You'll have to know how to use the formulas, so obviously you'll have some word problems that you'll be responsible for. And we're going to have about 15 multiple choice on that. For universal gravitation, we're going to have 2 free response questions, and it's going to be important that you're able to calculate the force generated between 2 objects using the formula for universal gravitation. So we're going to talk briefly about universal gravitation at the very end of these notes. So that's kind of what you can expect to see in the upcoming test. Alright, so let's go ahead and get started with describing velocity of an object that's undergoing uniform circular motion. So the velocity for objects traveling in a circle is pointed in a direction that is tangent to the circle. If we look over here to this circle, you'll notice that these points of the object, they have a vector for velocity coming at a tangent, which means it's perpendicular to the center of the circle. We could draw a right triangle here and it would be perpendicular to the center. So every one of these vectors is a tangent along that circle. The velocity of the object wants to go this way, but there's going to be something that's keeping it in a circle. In this case, we can look at this man throwing the shot put. He's got a rod that's holding this shot put to him. So as he swings it, this rod keeps the shot put in a circle, and you have this velocity vector for where the shot put wants to go. It wants to come straight ahead, but because he's holding it with that rod, it slings it around. Okay, so it says, where does he release the hammer to make it travel straight? Well, when he's spinning this, where do you think he would release the hammer to make it go straight? Right, you should have answered that he should release it at an angle perpendicular. So when he's swinging this around, maybe right here, he'll release it, and then it would go straight out through that opening in front of him. All right, so another important thing to note is that the velocity for objects in circular motion will increase if you increase the radius from the center of the circle. So as you get further away from the center of the circle, you're going to increase the speed that you're traveling. We talked briefly about how this works with different rides like the merry-go-round and stuff like that, where as you get further away from the center, you would increase the speed that you're traveling. Obviously, this isn't a good thing if you don't want to get dizzy. So if we look at this example here, it says you don't see this man holding the ball close to him to throw it. He's trying to maximize that velocity of the ball before he lets it go. So he's making sure he has full extension here so that he can get as much distance between him and the shot put. He's acting as the center of the circle here, and the shot put is the object that he's trying to accelerate its speed, right? So he's trying to get as much velocity as possible by increasing the distance or the radius for this circle as it travels around him. Alright, so the equation for calculating velocity of an object traveling in circular motion is right here. You have the average speed is equal to distance divided by time, and that's shown here by 2 times pi times r, because that's the circumference of a circle. And we would divide that by the period, which is the time it takes to make one complete revolution around the circle. Alright, so for uniform circular motion, the acceleration of objects traveling in a circle is pointed towards the center of the circle. So you'll notice in this diagram that the acceleration is pointing towards the center instead of alongside the velocity. And the reason for that is because even though you may have the same constant velocity as the object travels around the circle, it's actually changing direction. And because it's a vector, if you change the direction, even if you're not changing the speed, you're making an acceleration. And in this case, the acceleration will point to the center because as this vector goes around the circle, it's actually getting pulled back towards the center instead of going off in the tangent that it wants to go to. Okay, so it says the acceleration is pointed to the center, again, because that velocity vector gets pulled to the center. The equation for acceleration is right here. It's acceleration equals v squared over r, and v would represent the speed, r represents the radius, and the capital T represents the period. So if we rewrite this in terms of the equation we just saw for velocity and replace this v with that velocity equation, you would end up with 4 times pi squared times r over t squared. So it can be shown in both ways. Whichever equation you use will depend on what type of problem you're given. Okay, so the next thing you need to know about circular motion would be the force. And the force for objects traveling in a circle is pointed towards the center of the circle also because it goes in the same direction as the acceleration. Remember we discussed this, that the direction of your acceleration tells you where the net force is pointing. So if we look at this diagram here, you'll notice that the net force, this sigma f, is pointing in the same direction as the acceleration vector towards the center. If we look at this picture here, it says, I mean, you can see this person right here is trying to fly off this merry-go-round. These people are going really fast. And the force here is actually going to end up knocking him off because he wants to fly off to the side. We discussed that with the velocity. He wants to keep going this way. But because he's holding on, he's creating an inward force that's keeping him in that circle. Alright, so the formula for uniform circular motion force is going to be right here, F net equals ma. But if we apply what we know about circular motion, instead of an a here, we could replace it with v squared over r because that's our formula for acceleration. We can further simplify this to replace the v with the equation we had for velocity, so it would be F net equals m times 4 times pi squared times r over t squared. Again, m would represent mass, v represents speed, r represents radius, and t represents period. Okay, so this is like a rudimentary, if you look at this, a rudimentary gravitron. If you were to go to the carnival, you've probably seen these types of rides where you would get in, and as it rotates and increases its speed, you get lifted up onto the wall because you have a certain amount of force pushing you inwards. You get stuck to that wall. Alright, so a practice problem. It says calculate the period, velocity, acceleration, and force for an object traveling 2 rotations in 60 seconds if it has a mass of 10 kilograms and it's traveling at a radius of 1.3 meters. So it says here that a hint is to the period is the time it takes for 1 rotation, so just divide the 60 seconds by the 2 rotations to find that time. So if we go ahead and do the given here, the first thing you can put in there is the period. And we know it's 60 seconds and 2 rotations, so the time it takes to do 1 rotation would be that 30 seconds. We know that the mass is 10 kilograms. We know that the radius is 1.3 meters. Okay, we know our unknowns here are going to be period, velocity, acceleration, and centripetal force. So let's go ahead and solve for those 4 things. Again, we've already solved for the period. It's 30 seconds, so we don't have to actually use an equation for that. We will have to show an equation for these, though, so let's go ahead and do that. So for speed, we'll use that average speed equation, distance divided by time, or 2 pi r over t. And if we plug in our values for that, it would be 2 times pi times the radius of 1.3 meters divided by the period of 30 seconds. And that would give us a solution for the velocity of 0.27 meters per second. Now, if we had to calculate the acceleration, we would use the acceleration equation, v squared over r, or it can be written as 4 pi squared times r over t squared. And we'll be using this first one since we already know the velocity is 0.27. So it'll be 0.27 meters per second squared divided by the 1.3 meters of the radius. And when you put that into your calculator, again, remember that you need to make sure you square this first. You would end up with 0.06 meters per second squared, so that's the centripetal acceleration for the object. And then the last equation would be for force, and we'd use that F net equals ma. We've already solved for the acceleration, so we'll use this first equation instead of one of these other ones. And you would end up with force equals 10 kilograms, the mass, times 0.06 meters per second squared, the acceleration, and that'll give you a force of 0.6 newtons. Okay, so we're going to go ahead and finish by talking a little bit about the universal law of gravitation and Kepler's laws. So this is the equation that helps you calculate gravitational force existing between two objects. And it's right here. F grav is the force of gravity. Big G is a universal gravitation constant. It's always the same number, 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. And that will always be the number that you put in for this big G. M1 is the mass of the first object in kilograms, M2 is the mass of the second object in kilograms, and we would divide all that by the distance squared. And again, this distance is the distance between them. So this is how distance and mass affect gravitational force with regards to what happens when you change one or the other. So it says the effect of mass on force of gravity. So as you change the masses, we're going to see how that affects the force. Again, you'll notice that all the distances here are the same. So if we have equal masses, you have a force. If you have one mass that's double the size of another one, you would multiply the force by 2. If each one was doubled, then they would multiply it by 4. And then if you were to take one and triple its size, you would triple the force. So you can see that it's actually just the product of the two masses. So here 1 times 1 is 1, 1 times 2 is 2, 2 times 2 is 4, and 1 times 3 is 3. So as you increase the mass, however much you increase it by would be the same amount that you increase your force by. If we go over here to see the effect of distance on the force of gravity, it has an opposite effect. You'll notice that all these masses are the same. And if we look at this first one, again, everything is 1, so the force is 1. Over here, if you double the distance, you actually take a quarter of the force. And the reason for that is if we go back to the equation here, you're taking d and you're squaring it, right? So if it's 1 over 2, it would be 1 over 4 because that 2 would be squared, okay? Likewise over here, if we take 1/2 d, if you take 0.5 and you square it, it ends up making it so it's 4 times the force. Right, so let's take a look at a universal gravitation sample problem. It says determine the force of gravitational attraction between the Earth and a 70 kilogram physics student if the student is standing at sea level, a distance of 6.38 times 10 to the 6 meters from Earth's center. So basically the solution for the problem involves substituting known values. In this case, our given would be the gravitational constant, which is 6.673 times 10 to the negative 11th. And the mass of the Earth, right here, 5.98 times 10 to the 24th kilograms, times the mass of the second object, the 70 kilograms. I'm sorry it says that, but it's times 10 to the 24th here. Should be an exponent. If we actually plug these into the equation, it would look like this. The force of gravity is equal to 6.673 times 10 to the negative 11th times the 5.98 times 10 to the 24th kilograms, the mass of the Earth, times the mass of the student, 70 kilograms, divided by the distance between them, right here. So this ends up being 686 newtons for the force of gravity on that student. All right, and then the last thing, Kepler's laws. You're not going to be responsible for knowing anything but the concepts here. You just need to know that for planets, the path of the planets about the sun is elliptical in shape, with the center of the sun being located at one focus of the ellipse. And we'll talk briefly about this a little bit later. You'll be looking at an article that has some good diagrams for this. And an imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal intervals of time. This is the law of equal areas. And then the ratio of the squares of the periods of any two planets is equal to the ratio of the cubes of their average distances from the sun. This is the law of harmony. So I'm going to give you some diagrams that further explain this on Friday, but I kind of wanted to introduce it to you so that if you wanted to, you could do some independent research before we actually get to that. Alright, so that concludes the notes for today. Again, you're going to have some free time to finish these problems. A lot of these problems go off of the equations that I gave you, and if you have any questions, like I said, I encourage you to email me and I'll get back to you as soon as I can.